Hello, my name is Denise Bunk, and I'm the National Specialty Leader for Oxidation and Disinfection for Brown & Caldwell's Drinking Water and Reuse Practices. I'm also the incoming president of the International Ozone Association Pan-American Group because I'm passionate about the correct application, design, and safe use of ozone in water treatment. I'm extremely excited about working alongside Newton County to evaluate ozone for the Cornish Creek facility, and if ozone is selected, to lead the design effort and see the facility constructed and operating well, accomplishing many water quality goals. Ozone is an unstable gas that's generated on site and then dissolved into the water. It's a very strong oxidant, 50% stronger than chlorine, and that gives it an advantage over other water treatment chemicals. The way ozone reacts with water is dependent on several parameters that are unique to the water source. These include pH, alkalinity, and temperature, along with the amount of natural organic matter in the water and dissolved metals. So a critical part of determining whether ozone is the right tool for a particular facility is to evaluate how ozone reacts with that facility's water. To do that, we collect a sample of water, take it back to the lab, and conduct bench tests. We call it a bench test because it's conducted on the lab benchtop with a fixed volume of water. In contrast, a pilot test uses a continuous flow of water to a very small treatment plant, and that's usually located at the water source. While piloting is ideal, you can still get a lot of really valuable information from a well-designed and executed series of bench tests that capture the water quality from each season. Knowing that the contract would not begin until the fall and that the 60% design needed to be done in 9 months, we really wanted to capture the summer lake water quality conditions at Lake Varner to aid in the design. To do that, we needed to collect the water and run the bench tests at our specialized treatability lab. So our local field team, Ryan and Micah, launched from the boat ramp and headed over to the dam near the plant's 2 intakes. They had a multi-parameter sonde with them to collect data for a vertical profile. That helps us understand what is happening in terms of water quality from the lake surface down towards the bottom of the lake. From our data, we could tell that on August 22nd, the lake was still stratified, meaning that the upper layer was very warm, 85 degrees Fahrenheit, but then it transitioned to colder water ranging from 60 to 68 degrees, starting about 20 feet down. This colder layer had really low dissolved oxygen, or DO, less than 0.5 milligrams per liter. This is important because this anoxic condition allows nutrients such as phosphorus and nitrogen to be released from the sediment back into the water column. These nutrients in the water can support the growth of algal blooms. Low DO is also not good for fish populations who typically need DO levels of 5 milligrams per liter or higher. One of our innovative ideas for the ozone system is to consider using the gas collected from the top of the ozone contactors to add oxygen to the lake. This gas is about 98% oxygen and would normally just be released to atmosphere. At Cornish Creek, reusing this gas could have positive impacts on the lake by increasing the dissolved oxygen levels. Our field team collected water samples at depth using a weighted double check valve bailer. The bailer is about 3 feet long, and it was lowered down to a top depth of 12 to 13 feet. When it is pulled back up, the check valves close to capture the water at that depth. Then the water from the bailer is poured into the sample containers. We collected 10 gallons of water so that we would have enough for a lab test. We also collected water samples near the shore that included some of the sediment. Our goal was to capture enough plankton to be able to see its motility under 5 to 10 times magnification back at the lab. We packed up the samples and Micah drove them to our treatability lab in Nashville, where the bench tests were conducted that day. While Micah was on the way, our chemist Danny made the ozone stock solution to be used that day to evaluate different ozone doses. Recall that ozone is a gas that needs to be dissolved into water. For a batch test, we create an ozone stock solution by bubbling ozone gas into ultra-pure water until we reach a very high dissolved ozone concentration. We keep that concentration stable by using a water-jacketed reactor to keep the stock solution very cold. In this test, the ozone concentration was 40 milligrams per liter in this stock solution. Then we can precisely dose this liquid ozone stock solution into our samples to test different ozone doses. We ran 4 different tests on the raw water. In one jar, we tested 1 milligram per liter. In another jar, we tested 1.5 milligrams per liter. In a third jar, we tested 2 milligrams per liter, and in a fourth jar, we tested 3 milligrams per liter. The first part of what we wanted to find out is how much ozone is used in the first 30 seconds. This is called the instantaneous ozone demand. Secondly, we wanted to see how fast the ozone residual decreases over time. This is called the decay rate. You can see the curves generated from each of these tests on this graph. These values are particularly important in sizing an ozone system to know how much ozone generation capacity you need. That's how you size the equipment, and how much contact time you need. That sizes the basin or the contactor. In summer, the ozone demand and decay rate are typically the highest because the temperature is the highest and the amount of organic matter is typically the highest. So that is why it was so critical for us to capture this summer data, better informing the design effort early on rather than having to wait until next summer. In addition to testing the summer samples, we also chilled a portion of the water to test ozone demand and decay at colder temperatures. These tests will be rerun during fall and winter, given that water quality may vary along with the temperatures. But with respect to temperature alone, the results were as expected, with significantly lower decay rates at the colder temperature. This graph shows the results for the 3 milligram per liter dose for both warm and cold water. Note that the initial ozone demand was much lower at cold temperatures, and the ozone residual was measurable for over 30 minutes. This picture, showing the various shades of blue, are samples collected over time after the ozone was dosed. The ozone residual in the sample is related to the amount of bleaching of the solution. The sample on the left was collected just 1 minute after ozone was added, and it bleached out almost all of the indigo solution. At 1.5 minutes, the ozone residual was lower, so it could not bleach out as much indigo. And you see, over time, the ozone residual decreases and the bleaching effect lessens, resulting in deeper blue. An instrument is used to measure the color, and then we determine the ozone residual using a precise calibration curve. Besides generating the ozone demand and decay curves, we also performed another test looking at ozone's impact on zooplankton in Lake Varner. We found that the 2 nearshore sample bottles had the largest quantity of visible organisms. Many appeared to be copepods, but there were also other zooplankton. To maximize visible organisms for ozone testing, the remainder of the 10 gallons collected at depth was concentrated using a plankton filter, and the 2 nearshore sample bottles were decanted. The resulting volume contained a high concentration of zooplankton. This video shows that enough organisms were present and motile in the sample to observe changes with ozone treatment. Next, we tested ozone doses of 1 milligram per liter in 3 jars and 3 milligrams per liter in 3 separate jars. Several organisms were observed moving around in each of the 6 jars prior to ozone application. This video begins about 30 seconds after dosing 3 milligrams per liter. The swirling movement is from mixing the ozone stock solution into the sample. However, you can see one larger organism swimming against the current near the top of the screen. At the 2-minute mark, you can still observe movement in a few organisms, such as the one circling in the middle right quadrant of the screen. After 5 minutes, nothing can be observed moving in the 3 milligram per liter jars. In contrast, in the jars receiving only 1 milligram per liter, as shown here on the right side of the screen, motile organisms were observed throughout the 10 minutes after dosing and even the next morning. These qualitative results show that we are targeting the correct ozone dose range between 1 and 3 milligrams per liter, but identification and quantification of the organisms and their response to various intermediate ozone doses will be helpful in future tests. We look forward to conducting additional tests to capture water quality from other seasons. These tests, combined with our summer results, will allow us to confidently develop design criteria for Cornish Creek's new ozone facility while piloting is conducted in parallel.